Hello, welcome back. We're going to dive into trig functions next. If you viewed the previous podcast, you learned a little bit about the history of the trig functions, and then you also learned a little bit about the ratios and what they are. Basically, with the trig functions, if you have a right triangle, and let's say you have a right triangle that looks like this. And let's say on that right triangle you have an angle here, theta. And for now, let's assume that theta is positive. That angle measure is positive, and also acute. Okay, so we're going to just deal with acute angle, between 0 and 90 for now. And let's say that this particular right triangle has sides with length 12 and 5. Okay. And let's say that you were asked to try to identify what the values are of the 6 trigonometric functions for angle theta. Well, first of all, we really do need to know what the hypotenuse is of this right triangle. But we've dealt with that kind of problem before. With using the Pythagorean theorem, a squared plus b squared equals c squared. Remember, with right triangles, the sums of the squares of the legs is going to equal the square of the hypotenuse. So 5 and 12 can go in for A and B. It doesn't matter which one goes in for A and which one goes in for B. So let's say I say 5 squared plus 12 squared. And then C is the length of the hypotenuse, the longest side, or the side opposite the right angle. So we can plug the 5 and 12 in for A and B and then solve for C, and that'll give us the third side of the right triangle. So we have 25 plus 144 equals C squared. So 169 equals C squared. Now technically C is plus or minus the square root of 169. So plus or minus 13. But we're dealing with length here, and there's no direction specified, so we can just use the positive 13 for the length. So we'll go with positive because we're still with length there. But the Pythagorean theorem is a nice quick way of finding that third missing side. And that third missing side was important for helping us to find the 6 trig functions. Okay, so 6 trig functions. Let's start with sine. Sine of theta equals opposite over hypotenuse. So in this case, you're looking at theta. The side opposite of theta has a length of 5, and then the hypotenuse has a length of 13. So sine of theta is 5/13. Cosine of theta is adjacent over hypotenuse. So we're looking at theta. Adjacent is the side, not the hypotenuse, but the side, the leg attached to the theta here. So the length has 12, and the hypotenuse has length 13. I kind of remember cosine being close, cosine close, so adjacent over hypotenuse, versus sine being opposite or further away over hypotenuse. And then tangent of theta is opposite over adjacent. So we're going to have, from theta, you got the opposite side is 5, adjacent side is 12, so we get 5/12. And that takes care of half of the trigonometric functions of angle theta, 3 of them. Next we can do the reciprocals, the reciprocal functions. We've got reciprocal of sine of theta is cosecant of theta. So reciprocal, hypotenuse over opposite, so 13 over 5. Then cosine that's reciprocal is secant. Since they're 12 over 13, we're going to have 13 over 12. And then tangent, its reciprocal is cotangent. So instead of 5 over 12, we'd have 12 over 5. And now we've got all 6 trigonometric functions, the values of those. Now if you look at sine and cosecant, I remember that like sine starts with S, cosine starts with C, cosecant starts with C, secant starts with S. I just remember they're kind of matched with the opposite. Like sine is matched with the C, while cosine's matched with the S. You know, as far as doing the reciprocal functions. That's just the way I remember those, because it's not sine and secant together, like S and S, it's actually S and C and S. And then tangent and cotangent, I think you guys will remember, because cotangent has the word tangent in it. But there you go. It's a nice numerical example of what to do with trig functions. Now, some of you might be looking at this and going already a step further in your mind, going, well, what if theta isn't positive? What if it's not acute? You know, what do we do in those situations? I'm glad you asked. Let's use graphing grid to kind of explore how to handle that. This right triangle here, we got 12, 5, and 13. Let's go over to this graphing grid. And let's see, let's draw that triangle in quadrant 1. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I should say sketch it, because I'm not really going to use a ruler or anything. And then it was 12, 5, and 13. So 1, 2, 3, 4, 5. Okay, so let's do this. Let's try to make this kind of neat. I ran out of space on my writing tablet here. Let me try that again. There we go. And there we go. Okay. So we have this nice little right triangle. Right angles right here. Our theta had been right here. And we had had the 5, 12, and 13. So when we were doing our trig functions, our values, it was based on this theta right here. Okay. But what if theta isn't this acute positive angle? Or what if it's something else? All right. Well, let's say theta is obtuse. Let's say we have some kind of obtuse angle that starts here still and goes over to here. But let's say that wherever it stops, the leftover is the same amount of degrees as this theta here. So in other words, what's going to happen is this value here would be same as theta. And if we have that, we can draw another triangle on quadrant 2 and work with it to help us to figure out what's going on with this red theta here, with this big theta that's obtuse. Okay, so we can draw, let's say we have a triangle on this side. Let's say you got, okay, oops. Let's see, let me draw. We got 12. So 1, 2, 12. Okay. And then we've got 5. 5. And then got the hypotenuse right here. Hey, I didn't do too bad of a job sketching earlier when I was sketching theta. Not too bad. Okay. And then in blue here, this little theta matches that theta. But we're actually, what we're doing here is we're trying to figure out, let's say we're trying to figure out what's going on with alpha. Well, the values for alpha are going to be the same, the sine, cosine, tangent, etc. are going to be the same as if we took this triangle here and used this theta. Okay, we've got we've still got 12 units here, we've still got 5 units here, and we've still got 13 units here. But having this big angle alpha being obtuse, what ends up happening is this terminal side ends up being over here in quadrant 2, which means some of our signs are going to be different when we draw a triangle on this side. When we draw a right triangle where the end of this terminal side, we drop straight down, draw a perpendicular, and here we draw a triangle. But in this case, the x values are negative. So we have negative 12. This is y values are positive, positive 5. And when you do the Pythagorean theorem, you're squaring these two and adding them together, and then doing the square root length. So this is going to be positive 13. So when we go to do like the sine here, sine of alpha is the same thing as the sine of, let's call it theta primed. It's the same thing as sine of theta primed. Remember, sine's opposite over hypotenuse, so you'd have 5/13. Cosine of alpha, same thing as cosine of theta primed. That's going to be, this time, negative 12/13. Tangent of alpha, same thing as tangent of theta primed. Opposite over adjacent, it's going to be negative 5/12. So all of a sudden your signs are different, your SIGNs. Like where before, over here, sine of regular theta was everything was positive over here. Now we're dealing with where on the quadrant 2 the sine is positive, cosine and tangent are negative. But it's this wonderful thing because now we can deal with sine, cosine, tangent, and your cosecant, secant, cotangent of obtuse angles, because we've got this nice reference triangle over here in quadrant 2, where when you find the sine, cosine, tangent of this theta prime or this other theta, that will give you the same values as if you were finding sine, cosine, tangent of this obtuse alpha. Works out really cool. And it turns out if you want to have an angle that goes like this, it goes down into quadrant 3. And let's say that this segment that goes past the x-axis, let's call it theta double primed. Let's say that piece of the angle is the same measure as theta. Well, you can again draw a reference triangle down here in quadrant 3. Okay, I'm going to do that. Probably should do this in black since that's what all my triangles have been done in, but I guess it doesn't really matter. Okay, you can draw a reference triangle here by if you have this big angle, let's call it angle beta. Once you get past the 180, if this little extra amount going into quadrant 3 is the same as theta, you can draw another reference triangle, and you'll find here, okay, x is negative 12, y this time is negative. Well, hypotenuse is always going to be positive because when you're finding the hypotenuse, you're squaring these two and it becomes positive. So there, you're really finding like the sine of that beta is the same thing as finding the sine of this theta double primed. So sine opposite over hypotenuse, you're going to get negative 5/13. Cosine beta adjacent over hypotenuse, you're going to get negative 12/13. And then tangent of beta, you're going to get opposite over adjacent, negative 5 over negative 12, which gives you 5/12. And then last but not least, quadrant 4, we can work with it. Let's say we have some kind of crazy angle Takes us all the way around into quadrant 4. But let's say that this leftover piece in here, once we stop our angle, whatever the gap is, let's say that that's the same value, like this, just looking at those degrees strictly, be the same amount as this theta here. We'll call it theta triple primed. But if we draw a reference triangle, we can again see what our sine, cosine, and tangent should be. My sketching here is not the greatest, but close enough. Okay. And another reference triangle. This angle here is a right angle. So in this case, x is positive, y is negative, and the hypotenuse is still 13. So let's call that angle, call it something like delta. I'm running out of imagination here. Sine of delta. It's common to use Greek letters to name angles. I'm just right now running out of thoughts about what Greek letter to use. Alright, so sine of delta, opposite over hypotenuse, so we got negative 5 over 13. Cosine of delta, we've got adjacent over hypotenuse, so we got positive 12 over positive 13. And tangent of delta, opposite over adjacent, negative 5 over 13. Negative 5 over 12. Okay. So now you got 3 of the trig functions for those. And I didn't fill in cosecant, secant, cotangent, but keep in mind those are reciprocal identities. So, you take sine of alpha, do the reciprocal, you have cosecant. If sine is positive, the cosecant is going to be positive. Cosine of alpha, if you do the reciprocal of negative 12 13, you're going to get negative 13 12, and that's your secant. If the sine of cosine is negative, then secant is going to be negative. Whatever the SIGN is of sine, SINE, that's going to be the same for the cosecant. Whatever the sine is for cosine, it's going to be the same for secant. Whatever it is for tangent, it's going to be the same for cotangent. But notice there's a pattern here. Try to find a color I haven't used yet. In quadrant 1, notice that they are all positive. In quadrant 2, notice that sine is positive. In quadrant 3, notice that tangent is positive. And in quadrant 4, notice that cosine is positive. So as long as you know as long as you can draw a reference triangle, find your sine, cosine, and tangent, and then just pay attention to what quadrant you end up in, and then it's a matter of assigning positives or negatives, SIGNs. And a real quick way of trying to remember what signs, SIGNs, to use is starting in quadrant 1, think of the saying A for all, smart, S for sine, trig, T for tangent, class, C for cosine. So think about A, smart, trig, class. What you can always do is just draw a reference triangle. Your theta is that angle between the hypotenuse and the x-axis. That value is always going to be the same as this theta here would have been. So if you go and have a obtuse angle like alpha, just draw a reference triangle there where alpha ends, use that to figure out where to put your hypotenuse, and pay attention to what's happening to this little angle here where alpha ends, between where alpha ends and where the x-axis is. Or if your angle comes all the way over here in quadrant 3, just pay attention to what this little angle is here made between the hypotenuse and the x-axis. Or if your angle comes over into quadrant 4, pay attention to what this angle is between where where the orange ended, between that and where the x-axis is. Then you can draw a reference triangle. Use your sine, cosine, tangent knowledge, the whole opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, to get your fractions, and then assign the positives or negatives based on what quadrant the angle fell in. And then you can find these values for any of your angles. It doesn't have to be positive acute angles. It can be obtuse. It can be, or even if it's negative, you're going this direction. And you can pay attention, well, if you're going this direction, what's happening, and draw your reference triangle to help you to figure it out. So that's basically what's happening when you're working with these trig functions. Some of you might be looking at it though and going, well, what if we end up on an axis? Well, I'm glad you asked. What if you do end up on an axis? Well, then you're dealing with quadrantal angles. Like what if you have a 90-degree angle? How do you do your trig functions for something like that? Or what if you have a 180-degree angle or a 270-degree angle? What the heck do you do then? How does that work? Okay, so let's say you have a 90-degree angle. All right, and you want to try to figure out what's happening there. Let's say that you have, let's say you have an angle theta. It's in standard position. So in a standard position means initial sides on the positive x-axis, terminal sides somewhere out here. And let's say that the terminal side goes through (0,3). Excuse me. So 0,3 being right here. Alright, how the heck do we work with that? What do we do? Well, this is going to take a little bit of revisiting our trig functions. Earlier I talked about sine being opposite over hypotenuse, cosine being adjacent over hypotenuse, and so forth. And then we started talking about it on coordinate grids here. Notice that when we're dealing with sine, cosine, tangent, etc., not only are we dealing with opposite over adjacent and so forth, we're also dealing with x and y values. This 5, let's just focus on this triangle right here. This 5, that's a y value. That's straight up and down distance. This 12, that's an x value. That's a horizontal distance. And then 13, that's like the distance between the origin and this point here. We can go ahead and label that as r. We can use those labels to redefine what's happening with sine, cosine, tangent, and so forth. Okay. Got a right triangle here. That's y, that's x, that's r. This is theta. Well, x squared plus y squared equals r squared, based on the Pythagorean theorem. So if you want to find r, just take the positive square root of x squared plus y squared. Because we're just dealing with undirected distance, so just need the positive square root. But also, when you go to talk about sine of theta, not only is that opposite over hypotenuse, that's also y over r. Cosine of theta, not only is that adjacent over hypotenuse, but that's x over r. Tangent of theta, opposite over adjacent, y over x. And you have to be careful here, though, because you have to make sure that x isn't 0 in order for that to come out to be a real value. Cosecant of theta, reciprocal of sine, so you're going to get r over y. Of course, there you have to make sure that y isn't 0. Otherwise, it's going to be undefined. You're not going to have a real value there. Secant theta is going to be r over x. Got to make sure x isn't 0 in order to have a real value. And cotangent of theta is going to be flipped x over y. As long as y is not 0, we get something real there. So you can define it using x and y and r as well. It's the same ratios, just instead of labeling them opposite and adjacent hypotenuse, we're labeling them with like y, x, and r. But we can use that thought to help us too with a problem like this one, where they say, okay, let's say you have angle theta, terminal side goes through 0, 3. How the heck do you figure out your values for that? What do you do? Well, remember r equals the square root of x squared plus y squared. X squared 0 squared plus 3 squared. So r is the square root of 0 plus 9. Square root of 9, which is 3. And then we can use that to find our numbers. We can go through and say, okay, in that case, we got the distance of 3 here for r. Go back to our values with our sine, cosine, tangent, all of our ratios. We know that sine is y over r, so sine of theta is going to be 3 over 3, or 1. Cosine of theta is going to be x over r, so 0 over 3, which is 0. Tangent of theta is going to be y over x, 3 over 0. Uh-oh. Division by 0, that's undefined. So in this case, the tangent is undefined. Then when you go to do your reciprocals, cosecant of theta, just flip 3 over 3, you still have 3 over 3, so you get 1. The secant of theta, flip that, you get 3 over 0, so that's undefined. And then cotangent of theta is 0 over 3, or 0. So you can start handling the quadrantal angles doing it that way. And start looking at your function values that way. You've got some exercises where you have to play around with your function values for the quadrantal angles, and it's kind of cool how some of those turn out. So, try those problems and start looking to see if you find any patterns. But I'm sure you'll find some. Especially with a 0, there's going to be a repetition of zeros, ones, and undefineds. So just, go ahead and try out angles, try out a 180, try out a 270, and see where all of that gets you. So I'll pause there, I'll stop there so that you guys can do that and try some problems in general with finding the trig functions. And next podcast we'll continue this, and we're going to really get into identities some more, like how to figure how to figure more on going beyond just using the grid here and developing what's called identities or equal statements, and then using those equal statements to help you to solve more problems.